Hi, sometimes you can come across a sneaky little trap in a chip that you're using that can really make you come a gutser in your design if you're not careful and if you don't read the data sheets and specify your device correctly. Let's take a look at an example here. Let's take a look at the LM2776 switch capacitor inverter. Of course, this is like a variant of the classic R7660 voltage inverter. So the 7660 will be a classic chip if you want to invert a voltage rail, for example. Let's say you've got a 5-volt rail and you want to generate a minus 5-volt rail to power op amps, for example, and these 7660 type voltage inverters, I put that in quote marks because like 7660 is like such a jelly bean component. Not only are there just, you know, XXX 7660s, but there's many variants of these voltage inverters. It also does voltage doubling, by the way, but typically people use them for voltage inverters. When you've got to go from, say, you've got a 5-volt rail and you want to generate a negative 5-volt rail because you've got an op amp in your circuit, you want to power it, and stuff like that. It's a very common requirement. So you might use one of these 7660 voltage inverters to do that. Typically, you don't need a lot of current on negative rail of an op amp, for example. You might only need a couple of milliamps, you might need, you know, microamps. Occasionally, there's a couple of high current types, you might need a couple of 100 milliamps, which this one is. Look, it's 200 milliamps output current. But we'll take a look at that. So these 7660 voltage inverters, now, they're actually not that easy to find parametrically at the regular suppliers like DigiKey and Mouse. Let's take a look at DigiKey here. If you look at the categories down here, okay, there's DC to DC switching regulators, and that's actually where they're under. There's no category for these voltage inverters. So if you actually go in to, here it is, DC to DC switching regulators here, and you take a look at the function, the topology here, they're basically like really isn't, like, they've got an inverted one here, step up / inverted, which you might think's the case, but you've only got 3 parts remaining here, right? So like, so we can apply the filter, and of course we just end up with these 3 from Rome Semiconductor, and they're not what we want anyway. So you can't sort by function there, but if you go over to topology here, and you have a look all the way down, all the way with LBJ, you've got a charge pump down here and 126 devices. So we can actually get, and bingo, your 7660s will actually come up. But the problem is that we're literally only getting the 7660s here. We're not getting your more like specialized parts that, look, it's pretty much only 7660s, whereas you wouldn't find the one that we're actually looking at, that Texas Instruments one, you wouldn't find any of those more specialized parts. So even this subcategory for the charge pump, it just says charge pump, doesn't say charge pump inverter, just charge pump, doesn't actually find all the parts available, and that's not always a good thing. Now, Mouse is actually potentially a little bit better here because, look, you won't find them in here, okay? They don't have the product type in this list here. You've got to know to go into switch-in voltage regulators down here, and then if you get into switch-in voltage regulators, bingo, you do get the topology field, and you get your boost, inverting, SEPIC, but you don't want that, really. You're more interested in your, well, you could get your boost inverting ones and stuff like that, but, you know, you can start selecting those, but you can select, you've got charge pump and you've got inverting, for example, so we can apply filters. We've got 325 matches remaining, ta-da, and this one does show up a few other switch-in voltage regulators. It does show up, you know, more of your other parts, and you will get, which we'll see later, some of the parts down here. So you can get there, but it's not particularly easy or obvious, and you can potentially miss a lot of parts out there that might otherwise be the best choice for your application. And you might stumble across something like this LM2776 switch capacitor inverter. Might look like it does the business, you know, you might need a few tens of milliamps output or something. It's got a high switching frequency here, 2 megahertz high switching frequency, which based on the classic 7660 design actually implies a low output ripple. So if we go over to the classic 7660 here, trust me, I'll get to the point eventually. The trap with this chip, I'm just taking a tangent here. Now the classic 7660 can be a very efficient chip, or like near 100%, like 99% plus, but it depends on the switch in frequency. It depends on the output impedance of the switches inside the chip, because we have a look at the topology down here, like basically, they've got these output switching. It's switch capacitor voltage inverter. That's how it works. It switches the voltage on a cap and can invert or double the signal depending on how you wire it up. So the impedance of those switches there, also the amount of output capacitance, because you're going to have a typical circuit down here like this. So generally, like this capacitor here, which is always called, generally always called like C2 in this circuit. This is the switching capacitor over here, but this one determines how much ripple you ultimately how much ripple, but it depends on the frequency, the internal resistance of the switches, the ESR of the capacitor, and so forth. A whole bunch of things. So that's why generally in most 7660 data sheets, you will not actually find a voltage ripple graph. Like, you won't actually find ripple in any of the y-axes here versus, you know, output current. You'll find output resistance here, and you can see how the output resistance changes with the oscillator frequency and the oscillator capacitor value in here, for example. So the higher the capacitor value, that's C1 value, and it changes with temperature and all sorts of stuff, but they generally won't give you a ripple thing. That's because to actually get the ripple, you've typically got to, you know, there's quite a complicated little formula here that takes into account the ESR of the capacitor, C2 there. For example, the output current, of course, the higher the output current, the more ripple you're going to get. It takes into account the frequency of operation and all sorts of things. So generally they leave it up to your own devices, but there are a couple of data sheets that will actually show it. So one example would be the Maxim chip here, which is the ICL 7660/MAX1044, basically, you know, pin equivalent type thing. So we can go down here and have a look, and they will actually give us, thank you very much Maxim, a very nice output ripple here, output ripple in millivolts peak to peak here versus load current. In this case, well, why have they got two different load currents, 0 to 10 and 0 to 40 here? And with load, yeah, they've got two different graphs. Good on Maxim, very comprehensive. Anyway, you can see that this A graph here is with this boost mode, which is a frequency boost mode. So the higher the frequency, it's got a pin on there, you can just boost the frequency up. So the lower the ripple, you know, so at 10 milliamps output current, you might get 50 millivolts peak to peak ripple here. And but that will change if you just use the ICL 7660 version on its own. You'll get B, you'll get 200 millivolts ripple and so forth. And that's for a nominal output capacitance of 10 microfarads and a switching capacitor of 10 microfarads. So, you know, you can't, the first trap is that you can't just read these graphs and go, oh, I'm going to get 50 millivolts peak to peak ripple at, you know, like that's what the chip's going to give. No, it depends on the capacitance, but also what the ESR of the capacitor use and all sorts of stuff. So they don't actually go into that. So that's why these graphs can actually be a bit misleading. You might put your 10 microfarad cap in there, but depending on the voltage rating and the D rating of the capacitance with the DC bias on the capacitor, and like that's a whole video. Have I done a video on that? I don't know, I probably should. Anyway, capacitance can change with DC bias, and the type of capacitor, whether it's X7R or like a Y5U, a real crap Y5U class dielectric, for example, the capacitance can massively drop and not be, it might measure 10 microfarads on your LCR meter, but you're going to get diddly squat when you actually put it in the working circuit at the working voltage and whatnot. So, yeah, you can actually get those sort of graphs, but generally they won't give you that for a 7660. Anyway, let's get back to this and the trap with this LM2776. And you might think this is a great chip because you picked it because it's available, it might be the right price. Doesn't matter. right? Let's just say that you've found this chip, 2 megahertz switch-in frequency. If you're familiar with the 7660s, that might imply nice low output ripple and stuff like that. The higher the frequency, it's got lots of current capability. You know, sounds like a good chip, right? And it's available in like a little tiny 6-pin package, none of this 8-pin rubbish, right, that you get with the 7660. And so let's actually go down here and have a look. And they actually do give you, this is one of the ones that actually give you the output ripple. They're actually like right off the bat. Look at this, fantastic. Now, if you look at this one here, right, you can see that output ripple versus input voltage. And you go, output ripple? Oh, look at that. 10 millivolts there, down at input voltage, but they don't tell you, yeah, I out at 100 milliamps. That's pretty good, right? At 100 milliamps output current. And that might be a killer, right? That might be fantastic compared to some other 7660 type ones out there, right? So you might think that's fantastic, but here's the trap. Look at this one over here, okay? Now, let's say you're operating at output current of 100 milliamps, right? 0.1 amps. Look, no worries, right? We've got 25 millivolts output ripple. Let's say that's fine for your application, right? But look what happens if you just drop it back. Well, let's say you're operating at like 60 milliamps or something there, right? But let's say that your circuit has different modes of operation, for example, or the temperature changes, because that's why we have 3 parametric curves here. That's what parametric curve means. It means you have a different curve for a particular parameter. In this case, the parameter up here is the ambient temperature. So the red one is nominal, right? So look, that's 20 milliamps, 30, 40, 50. So at like 60 milliamps there, right? You get like, let's say 70, you're going to be operating at, you know, 25, let's say 25 milliamps peak to peak ripple. But if that temperature changes, whoa, look, you go straight up this curve and you're screwed, right? Because you're suddenly dropped to another temperature thing, right? It's just nuts. So you might get one ripple voltage at a particular temperature, and then all of a sudden, wham, changes completely at a different temperature or a different output current. Let's say your circuit actually has, you know, two different current modes, and it takes more current in one mode than the other. The output ripple can like go up like 4 or 5 times, something like that, from 20 millivolts up to like 80 or 100 millivolts peak to peak, and that could really ruin your day. Unbelievable. So like, and you don't get that. You don't get this sort of sharp response that we saw over here. Look, this output ripple, right? It's just you know, pretty linear with your output current, because your traditional 7660s just have a single mode of operation. And here's the trick. LM2776 has a low current PFM mode operation, right? So if you search for PFM, devil's in the detail, PFM operation. To minimize quiescent current during light load operation, the LM2776 allows PFM or pulse skipping operation, it's pulse frequency modulation, by allowing the charge pump to switch less when the output current is less than 40 milliamps. Bingo! And that's what we saw with that big rise in the output ripple there, because it's completely changing modes there. It's changing frequency. So they do this to minimize the quiescent draw from the power supply, and that might be great for your application, you know, if you're really trying to get lower that quiescent current. But as I said, most of these things are, you know, it depends on where the frequency you use them at. They can be very, very efficient, but you've got to pick the right thing. And by the way, the before I mention it, the 7660, it does have an oscillator pin on here, and you can generally either leave that where's the example app? Here we go. You can either leave that open, or you can put a external capacitor on here to select your operational frequency, or you can override it by feeding in an external clock. And that's really good if you've got like analog to digital converters, sampling systems, and you don't want other chips in your system, just especially switching regulators, switching converters, switching inverters, stuff like this, DC to DC converters. You don't want those running at just any frequency, you know, higgledy-piggledy, right? Because that can interfere with, of course, switching components inside your sampling system. So often you want to synchronize the clock with your sampling clock, and then that can eliminate, then your converter, your ADC, can actually do a real good job at eliminating those frequencies, those switching frequencies out, all that noise on the rail. So you can often override there, but anyway, the frequency of pulsed operation is not limited and can drop into the sub 1 kilohertz range when unloaded. And as the load increases, the frequency and pulsing increase, and so it transitions to constant frequency operation. There we go. That's what we see there. Wham, bam, thank you, ma'am. Not sure, like right down here at like really ridiculously low currents, it can change a lot too. Even that can ruin your day. Going from 80 millivolts might be acceptable in your design, because you might be post-regulating this thing, either using a low dropout regulator, or you know, a Zener, or even just some you know, RC or LC filtering, or something like that. But you know, going from 80 to 120, that could ruin your day too. So at light loads, so you've got to be, you know, got to be really careful with this thing. So you can really come a gutser with a chip like this that has different modes of operation, especially if voltage ripple is important to you. Because look, you go up the top here, applications, data converter, power supplies, right? You might think, you might see this, you know, banner app here. These are almost always bullshit kind of thing. They just, marketing just throw these terms in there just to say, you know, try and cover all the bases, because engineers see, you know, a lot of them will see this and go, oh, it's perfect for data converter power supplies. I'm on a winner, I'll use this chip. But of course, it can have a horrible amount, unacceptable amount of output ripple. Audio amplifier power supplies, yeah, that's what you want. Huge amount of ripple on your audio amplifier power supply. You know, it's just like operational amplifier power supplies and stuff like that. So if you've got your negative rail, using this to generate the negative rail of your power supply, and you've got, you know, 100 millivolts of switching noise on your negative power supply rail, that can ruin your day. Because you know, your power supply rejection ratio, your op amp may not be that great. So there you go. That's a real trap, these dual mode converter chips. Just watch out for it. So in this particular case, like, because these parametric searches on DigiKey and Mouser aren't that great, this is where one example where you might want to go over to the manufacturer's website and use their parametric tools or their product categories. In this case, if you go over to TI and you go into power management devices, you know, you got all your LDOs, but under the switching regulator ones, we do actually have a category down here. We've got a boost charge pump, inductorless, and we've got a buck boost or inverting charge pump, inductorless 34 here. So if you go into that category down here, bingo, you get all these chips down here. And of course, one of them is our friend of the LM2776 here, the switch capacitor inverter. And just based on that, you might think, hey, this one's fantastic. It's equivalent to a 7660, but it ain't. It's got those different modes of operation that you can really come a gutser on. But I actually like the look of some of these other ones. Check this one out. Low noise, regulated inverter with integrated LDO. Oh yeah, now we're talking. So let's have a look at this bad boy here, because one of the things you might want to do, of course, you might use this 7660 inverter, which, by the way, it's such a jelly bean part, the 7660, that if you go to AliExpress or something like that, they're available in tons of different one-hung low brands, genuine or not, doesn't matter. In the case of the 7660, it's probably not a major risk in terms of getting, like, you know, counterfeit parts and stuff like that, unless they physically don't work at all. Because really, the you know, the spread of operation of this thing is and the topology is so sort of wide that, you know, pretty much anyone's going to work the 7660, especially at like low currents and stuff like that. If you're only drawing a milliamp or something like that, pretty much any 7660 will probably do the business. But of course, it might draw more quiescent current, it might not be as efficient, whatever. But, you know, generally you're going to be okay. But they might have a, you know, significant amount of output ripple, because you can only do so much. You can't put an infinite amount of capacitance on that with that C2 capacitor on the output, because at some point the ESR of the capacitance is going to take over. You're going to have a really, well, a minimum amount of ripple that you can get rid of, right? That you can reduce the ripple to before the ESR of the capacitor starts going up, because the higher the capacitance for a given package size means that your ESR must go up. So then it reduces the effectiveness of reducing that output ripple. And as we saw in that complicated formula back there. So there's only so much you can do. You can't just put, you know, 1,000 mic in there and think that your ripple's going to zero. So you may have to do some post regulation. So you might put a low dropout regulator on the output of your 7660, for example, if you need a minimum amount of ripple. But there's a bit of a trap there using a 7660 and then having your post regulator on there, is depending on the voltage drop across that regulator. If you're only dropping the smaller voltage you drop, the less effective it becomes of filtering input noise and stuff like that. So if you only got a low dropout voltage on it, then your noise might pass mostly through that regulator. So, you know, you've got to be careful there. It's not a magic, putting a LDO on the output's not a magic bullet. So let's have a look at this bad boy. Inverter regulates the input supply voltage, low output ripple. There it is. Shut down lowest quiescent current, blah, 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 up to 250 milliamps output current. That's huge, right? That's enormous. Once again, 2 megahertz operation, high frequency operation, so it can get lower output ripple easier. So I want to see the block diagram of this bad boy. Where is it? Oh, come on. There it is. Output current, switched array, and then, yep, you guessed it, we've got an LDO. There it is. So, yeah, negative band gap, low pass filter, and then got a low pass filter here, and a voltage out. So, there you go. It's got integrated LDO. Awesome. Let's check the price on that, see if it's actually cheaper than this LM277676. Nah, unfortunately it's not cheaper there. In 3,000 quantity, we're talking 44 cents here for the 2776 and the 2761 with the integrated LDO. It's more expensive, needs greater silicon area. They can't get the yield on the not the yield, the the density on the wafer. So you pay for wafer space. So for 3,000 quantity, 82 cents. So you'd have to weigh up that. Maybe you could get. It might be cheaper to just go with the other one with an external LDO that you might get a Japan Radio Corp LDO or something like that, and cheap as chips, and do that. But once again, it may not be as effective. But this 2761, I rather like this. Like to have that LDO integrated, and what type of power in data, once again, power in data converters, interface power supplies, operational amplifier power, so, just generating a negative rail for your op amp and stuff like that. But here we go, output voltage ripple. Here's the money shot. Look at this, right? We're talking V in, at 3 volts, and V out minus 1.8. You're going to get higher ripple at the higher voltage. Supply, if you're going from 5 to negative 5, for example, but that's really quite good. That's under under 1 millivolt there. You'll struggle to get that kind of ripple with an external LDO. So that's it's doing really good, and of course that's going to increase with the increased output current. But even at 250 milliamps, anyway, there's no weird PFM operation mode where your output ripple just goes to buggery, and yeah, neat. But check out this bad boy here. Now we're just like surfing for parts. Sorry for the tangent, but you know, it's just cool. I like this one. Looks really groovy. Look at this. Generates low noise adjustable positive supply between 1.5 and 5 and negative supply between negative 1.5 and 5. So it's actually got dual regulators in here. Look at this. Wow. Fantastic, right? So for a single 5-volt in, you get a regulated output. So this could potentially replace, let's go down and have a look at the block diagram, potentially replace 2 regulators in your design. So you can put it all in one chip. So you can have so you can consolidate a 7660, some other positive voltage regulator you're using in your design, and the negative filtering LDO on the negative rail on the output of your 7660. So there you go. There you go. It's got two. It's got a negative one, and a totally separate positive one here by the looks of it. So that's really groovy. I like that. And unfortunately, if you go over in and look at the price, yep, you pay a bit more. Once again, it needs more silicon real estate, so it's 97 cents in 3,000 quantity. But hey, that could, and it's in like a little pain in the ass QFN type package, but you know, it's not a huge, but you might need that. You might need the density, right? And that could save you space and not potentially cost. You know, it might be if your main driving criteria is cost. You know, you may not use this part. But the problem with using these specialized parts is that there's one source. I bet you won't find another pin compatible one from another manufacturer with this. So that's the advantage of the 7660. You can get a jelly bean part from anyone, available, you know, it'll never become unavailable, really. And you can just use then standard regulators, which have a standard pin out. Once again, you've got a wide choice of manufacturers. But you might have demanding requirements like, you know, the ability to, like, you know, noise pass-through, dropout versus dropout voltage and all that sort of jazz. But anyway, there you go. TI have some interesting parts in that respect. So you don't often, as a general rule, you don't want to be locked into a specialized part like this if you can avoid it. But, you know, you may need it because you need the board space or whatever, or the size. So they've got some interesting parts in here. Look at this one. Low noise negative bias generator. Whoa. Well, here's a specialized part for you. Look at this funky thing. It literally, it generates a negative 2.32 volts. Why 2.32? Because you just need to be able to go to ground with an op-amp or some other part. So you can't power the part from like 0 to 5 volts, for example. You can't always get right down to 0. Either you can't sense down to 0 or you can't output down to 0. But if you have just a smidgen below, you know, 0.1 volts below ground, then your circuit can happily sense and output all the way to ground. So often you might just need something like this. You don't need negative 5 volts or negative 3.3 volts. You just need negative 0.1 or something like that. And that's exactly what this chip does. With an output ripple of 4 millivolts peak to peak, supply voltage of 3 to 5.25, 98% conversion because it's just driving bugger all. It probably only has like 10 milliamps tops. And it just generates a negative rail. That's all. There it is. Low voltage amplifier, for example, and true 0 output voltage. There it is. It actually tells you by generating a negative 0.23 volt rail. And that's all you need. So that's a nice little specialized part there. Geez, how much does that cost? There you go, 33 cents in 3,000 quantity. So that might do the business there. But once again, that's not going. Is that a pin compatible the 7660? Oh, for goodness sake! Like, just put the labels directly on here, not pin 1 through to pin 8 and then have a table. Just put the lazy ass. Whoever did this data sheet. Anyway, is that VSS ground pin 2? No, that's not a 7660 compatible pin out, I don't think. So yeah, you might be stuck there if you decide to use that part, but isn't it neat? So there you go. Anyway, I've waffled on enough. Sorry about that. I started out just wanting to show this trap here, and it might look obvious, you know. It might look real, look, well, there it is. The first graph in the data sheet shows you that. But, you know, if you're not paying attention, you look at this one, or, you know, you, whatever reason, you didn't notice this or didn't think about the changing mode of operation in this chip and what effect it can have on voltage ripple, especially if you're doing the famed data converter power supply or audio amplifier power supplies, where ripple is almost certainly important, and you can really come a gutser. Anyway, there you go. Traps for young players. Modes in chips. Jeez, gotta watch out for it. Oh, by the way, I just thought I'd shill my own product. I don't do it very often, so please forgive me, but it's kind of relevant. The micro sleeves. The micro sleeves are back in stock. I'll have to link in the video at the end of this if you haven't seen the micro sleeve. And it's a neat way just to hold your parts in a static protective thing. You can just slide your parts in there, label them all, and it's just a real handy way to do it. So yeah, it's just a really cool way to organize all your parts for a particular project. So you might have a folder like this for a particular product. In this case, we've got like schematics and other stuff in here. We've even got, I won't show you that, but we've even got like waffle trays and other parts taped inside here. So it really is quite handy. It didn't have them in stock for a while, but they're back over on the website, so I'll link it in down below. Check it out. Anyway, if you like that video, give it a thumbs up. As always, discuss it down below. And as always, you can support me on Patreon. I often release videos early on Patreon, so that's linked down below as well. Catch you next time.